I have wandered into C++ now. By the way, it's not my first time in Aspen, but it's my first time speaking here, so thank you. Great conference. It's been going on for the better part of 20 years. It'll be the 20-year anniversary and a few more. But one thing I want to say is I've noticed something a little different this year. There's almost every slot today, and that's going to go through to this evening, has something to do about successor language or future of C++ or something that C++ could evolve into. And I think that talking about future and about evolution is a wonderful thing, and more experiments are better. This was set up, I added a couple of chairs, but this was set up when I got here, and isn't it taking it a little too far, though, to set up 13 chairs? I mean, this is not the Last Supper for C++ yet, all right? Having said that, so thank you, Bob, for that intro. Let me give a very brief recap, especially for those who may not be aware of the project. There are many like that. But I'll try not to repeat what I've said in my CppCon talk from last fall, but a quick recap of what some of the highlights are that are important to me. Then most of the talk is going to be talking about, well, what's new? And a lot of this, but not all, has been covered in the blog post that I posted last week, the 4-month update as to what's been new since January. But then I really want to spend some time talking about compatibility and different aspects of it. Why compatibility is important, but what kind of compatibility is the kind that we really want and benefit from. And then what plan does that choice put us on? Because there's more than one plan, there's more than one playbook. There are tens of thousands of programming languages in the history of our short industry. Our industry's been around a few decades, barely over half a century. Only a few dozen have achieved widespread commercial use, say, call it roughly 1 million users and up. Why have so many failed? Some were narrow niche languages, but experimentation is good, but how can we succeed? How can we especially succeed in doing something that has been tried before, it looks like, and what's different now? So here's the recap. Mostly this is a couple of copies of slides that I already gave. So I think it's great that experiments are going on the left-hand side of the screen about new languages, new ecosystems, new module systems, new concept systems, and compatibility bridges with C++ today, or just C, and that's a fine choice too. My interest, though, is in exploring how can we refresh C++ itself rather than creating a competing thing. And spoiler alert, anything that looks different will be interpreted as a competing thing. So part of this talk is to convince you why I don't view it that way, but I understand if others do, even my project. But I'm interested in making the C++ guidance we already teach the default, making C++ modules we already have in C++20 the default, keeping our entire existing ecosystem, our entire compatibility with our code base. And when I say compatibility, I won't say it every time, but I mean I can call any C++ code that exists today pretty much without limitation, including macro and SVN compatibility, with no shims, no thunks, no overheads, no indirections, no wrapping. I'm talking about the level of compatibility that each successive release of C++ has had with the previous one. So my goal for C++ compatibility is same as C++20 was to 17, and 17 was to 14, and so on. How can we take a breaking change? There is no way we can take a breaking change. We can't even change a default without breaking the world. If we apply it to existing code, we can't change the meaning of existing code. So what if, this is the experiment, and like most experiments, the default is failure. But we should at least try, I think, to say, what if we had a bubble of new code that was an alternative syntax, a syntax 2 for C++ itself, where we could not just change syntax because to make it pretty, that's not interesting enough, but change semantics, change defaults, change generated functions, change the way the pieces work together to factor the language into a small number of orthogonal composable components. that's 10 times easier to teach and learn and remember and use because there are just that many fewer special cases and warts and interactions to have to remember by rote. To make it 50x safer, and by that I specifically mean reduce by 98% the number of CVEs in 4 specific safety categories, reported vulnerabilities in type and memory safety in 4 specific categories. And you know, we've done something like this before. Of all the releases of C++, to me, the most monumental one has been C++11. Yeah, 20 had lots of big stuff in it. And 98 was the first one that actually codified the standard, but it codified what we had. And it added templates and exceptions, but we'd been using those in pre-standard compilers. C++20 adds coroutines and modules and concepts. Really good. C++11 changed the way we wrote our code. It had auto and lambdas and so many different things, trailing return type syntax, which if the C++ committee hadn't said, this is what we're doing, people would have had antibodies all over the place. Oh, that's foreign, that's not C++. And then WG21 said, it's C++, and everybody said, it's C++. Which is proper, because it's WG21, not any company, not any individual, even a member of WG21. It is the whole committee who says what the standard is, by consensus, and that's really important. But what if we could do C++11 again, which felt like a new language? Bjarne described it that way correctly. But instead of C++11, where we did individual upgrades, individual feature here, feature there, and then the whole thing, that added up to feeling like a new language. What if we actually refactored the whole thing and tried to do the job across the language and come up with a directed evolution of C++? So this is my personal experiment to learn some things, to prove out some concepts, share some ideas. I showed this slide about 7 months ago, and I said it's hilariously incomplete. It only has functions. Turns out you can get pretty far with just functions. Since then, we've added other things, and I'll talk about some of them today. But the goal is to start a conversation about what can we do within C++'s evolution without leaving 100% backward compatibility whenever we want it, but also not pay for it if we don't use it. I'll add to this slide just to summarize. When I showed this, this was true and it's still true. This already works with every major C++ compiler. Every major C++ compiler can build cppfront and can build the executables, the cpp1 files produced by cppfront. So thank you, first of all, to over 100 folks, the hundreds of issues, the hundreds of PRs, since I first talked about this at the other conference, and more that aren't on the screen who contributed in private emails, in comment threads. These are just the ones who opened issues and PRs, so thank you. So here's a summary in one slide of all the features I demonstrated last time. And they are in 2 buckets, really 3, because one of them is compatibility. That's always implicit. But the 2 main buckets are safety. The goal is 50x fewer CVEs because of type, bounds, lifetime, and initialization safety. And so those are the features I showed. And I bolded guaranteed initialization before use and also out parameters, because I'm going to recap that a few slides from now and then build on it, because that is central to the special member functions. We'll show what that means. I also talked about simplicity. And again, all these things were implemented and live demoed, is and as, pattern matching with inspect, unified function call syntax, uniform capture, including string interpolation as well as lambdas, and a context-free order-independent grammar, all of those things. But also 0 overhead backward compatibility. So you always have link compatibility. And you have source compatibility always available, but you only pay for it if you need it. And the way this works is that you can write a standalone syntax2 file, and that's fine. You're programming in a 10x smaller language. Or you can interleave sections of CPP1 and CPP2 in the same source file, not nested within each other, but side by side, and that's perfectly fine too. And then you're programming, then you have to go long-term through a full C++ compiler, but you're paying for it only if you use it. Perhaps someday, if it succeeds, syntax2 might have smaller, faster compilers that only can deal with syntax2. But that's the kind of idea of applying the 0 overhead principle to the language itself. And I've been bringing these as proposals, as evolutions of today's syntax for the last 7, now 8 years. So that's the recap. Now let's talk about what's new. And this is mainly going to be about types and reflection and metafunctions, but there's also some smaller features, and it's a nice segue as we talk especially about the unification of the types and operator equals. So first of all, out of all those proposals that I've brought from this work as incremental, as individual proposals to the C++ Standards Committee and to conferences to see, hey, does the committee and the community agree that's a problem worth solving? Even if yes, do they agree with this kind of shape of solution? And thank you very much for all the feedback. For example, when I show metafunctions in a little bit, you will see direct influence, especially when I show my original proposal with what I actually implemented. What I'm actually implementing is much closer to what SG7 gave feedback for. So thank you for all the feedback in the community and the committee. But one piece of this has already been standardized. So the first piece of CPP2 that is already ISO C++ is the spaceship operator and unified comparisons. And I'm going to use that as the first example of simplicity, safety, and efficiency not always being in tension. How many of you, we know that these things are sometimes in tension, right? Everybody agrees with this. Not a single hand went up. It's like, yeah, motherhood apple pie. I saw the nods. How many of you would agree that they're very rarely actually in tension? A few hands, and the longer I wait, the more slow risers. Is it safe? Much of the time, especially if you pick the right abstractions, these are not in tension. For example, since the early days of C++, we have been producing results. Bjarne and Alex Stepanov have been producing results showing the performance of templated algorithms being faster than for loops in C. Why? Because you're expressing your intent at a higher level, and optimizers love you. So that's an example of how expressing intent more directly than the nuts and bolts of step-by-step, the cookbook, how to do it, is easier for us to express. That's simpler. It's easier for compilers to optimize because they can see, oh, that's what you're doing. Well, here, let me help you, which is more efficient. And safety plays in with both of these too. So since we should, oh, that doesn't look like 3 stripes on this particular screen once I put it together. Those colors look the same. That's supposed to be a 3-color flag that we're now going to use, which I don't think is the same as any country's flag because I don't think anybody uses pastel colors. To say, yes, here's how we can do all these 3 things at the same time. And the first example is the one part of the spaceship proposal that has not yet been adopted. So I've implemented it in cppfront, and that is chain comparisons. So as of, I think it was in January or in February, I implemented chain comparisons. And this is simple because I can directly express my intent. Min is less than or equal to index is less than max. I can say what I mean. I can say the mathematically sound ones, and that means the ones that are transitively true. So the sound chains mean that if I do A something, B something, C, they're not just pairwise true, but you can also infer something about the first and the third, the A and the C. That is not true of chains like this and chains like this, which, for example, are allowed in Python. But the documentation has clear warning labels. Don't do that. They will surprise you. They don't make the sense that you think they make. I had a chance actually last week. Ever since Guido van Rossum joined Microsoft, we work at the same place. We've been able to talk more regularly, which is great. For the past year or two, I can't remember how long it's been. I saw him just last week, and I'll show a picture in a minute. And I asked him, like, so is there a reason? I'm just curious. Why does Python not ban the mathematically unsound ones? And he said, well, it's really 2 reasons. First of all, you can overload them and people did funny things, and so we don't want to break that code. But second, we can never take anything away. It'd be nice to take that away because people make the mistake and we have to document it. But once you have it, you can't take it away. So when I implemented this in cppfront, I implemented only the safe ones. The other ones are compile time errors telling you exactly what you did wrong and why it's being rejected. So that's simple. It's mathematically safe. And it's efficient because I don't have to write min less than or equal to index and index less than max, which if index is an expression would be double evaluation, I get efficient single evaluation just naturally because I just wrote it a single time. So that's chain comparisons. Another example is named loops. So everything in CPP2 is name colon. That's how you introduce names. So it seemed natural to also have a name for a loop. And so you can have named break and continue. Other languages have this as well. And I got a little pushback, like, why have that? Isn't that a glorified goto? Yes and no. It's implemented as goto. It's efficient. It is safe because it's structured. And by the way, it reduces the demand for me to add goto into CPP2. By the way, heresy alert. Maybe I should take a seat at one of these 13 chairs at this point for what I'm about to say. I am not against goto. I would happily implement it in CPP2. No pitchforks. No pitch. Come on, boo. But not the C goto. I mean, C++ already made goto better because you can't jump past an initialization, right? If you didn't know that, C++ already has a tamer goto. There's nothing wrong with a structured goto, which only jumps forward or out and not across an initialization. It doesn't jump into the middle of a loop like Duff's device. It doesn't jump across an initialization, which C++ already disallows. And it doesn't jump backwards, which is an unstructured loop. Now you're creating spaghetti loops. Those three things are why the famous letter exists, that goto is considered harmful. That goto is, structured goto is fine. But if I have a few features like this that cover the use cases why you would want the unstructured goto, that's even better because now I can even more directly express my intent and maybe I'll never have to add goto. The third example is main. So I always showed arrow int at the last talk. That's now optional. It's implicit if you don't use it. You don't have to write a return or an arrow int. If you don't want the command line arguments, you don't have to ask for them. But if you ask for them, it's just a single variable args, which is implicitly of type vector string view, as it should be. Yes, I am thinking of you efficiency folks as well, because you bare metal folks will want 0 allocations, not even 1 allocation at the beginning of program startup if you get main. I'm considering adding an fno alloc, like I've already added an fno exceptions and an fno RTTI, that would instead give you something that doesn't do any allocations. So I might do that. We'll see what the demand is. It's possible to do. But this is simple. I can always express my intent. By the way, this is a complete program. I didn't have to import or include std. The standard library is just by default available. I can omit the arrow int. I can omit the braces around a single statement function, which I do here because I don't need to write them. Just a single statement. It's safe, including see that args0 that I'm doing string interpolation of the result of args0? That's bounce checked by default. So if I'd written 1, this program would have done a contract violation, and you could call an installable contract violation handler. And it's efficient because I pay for it only if I use it. This is the 0 overhead principle. If I do opt into args, I get one allocation, a single allocation for the lifetime of the program. So that's it for small things. Now let's talk about user-defined types. So everything in CPP2 is declared name, colon, kind equals value. My class is a type with value this body. Just like in the second line, data is an int32 with value this expression, and so forth. Print is a function with an explicit this parameter, because everything's explicit. Explicit is better than implicit. But I didn't have to say the type because defaults are fine. I know what type this is, so I don't have to say it. But print is a member function. It has a this parameter and no others, equal to this body and so forth. The explicit this is an alias, not a pointer. There's an alias for this object. And because I can apply the normal parameter passing, notice that first print is an in parameter, that's the default, which implies const, which means the whole thing is a const member function. I've said that by declaring the this parameter. In today's syntax, the grammar is complicated with warts on the end and before for virtual to say, oh, something is const, this member function is const, or that it's ref, that it's an R-value qualified member function, that kind of thing. Those are substitutes for not being able to talk about this parameter explicitly. In CPP2, we can talk about it easily, but explicitly. And so all the normal parameter passing applies to it. Add to data is in-out this. It's a mutating member function, therefore it's implicitly a non-const member function when we lower to CPP1. And the defaults for all types are functions and types, including nested types and base types, are public by default, and member data is private by default. One thing I've discovered in writing CPP2 code is I rarely write access specifiers. I still write them. For instance, there's some in reflect.h that I'm going to show you later on. But where I write protected in 2 places. But these defaults are great. At least they match my coding style. Your mileage may vary. There's also way less magic in generated functions. Every type must have a destructor. You can't use a type that doesn't have a destructor. So if you don't write one, we'll generate one. And the default constructor is generated if there are no constructors that you've written at all. But that's it. Everything else is opt-in, which means I might still in the future support equals delete, just to explicitly prune things out of overload sets. But I don't think I'm ever going to need equals delete to suppress generated member functions, because everything is opt-in. Everything is opt-in all the time. I talked about initialization safety. Here's an example from a slide I gave a few months ago. So the idea here is that in this function, I'm declaring x is a stood string, semicolon. There's no equals value. That means I'm declaring the name. I'm allocating enough storage for a string, but I'm not constructing it yet. And I then guarantee that it's initialized, constructed before it's used locally in the function. In the true branch, I simply say x equals value. And that's the same syntax for construction and for assignment. And in this case, because that's the definite first use, that constructs. That's a constructor call. Now, of course, I don't initialize it on the else branch, so I get the beautiful error message at bottom saying, no, you violated initialization before use, and we can diagnose that. So what happens if we fill that in? Well, one way to fill it in, and this is the segue to the unification of operator equals, is I can use out parameters. And out parameters are super important because every function like fill that has an out parameter is effectively a delegating constructor. It can take an initialized or an uninitialized object. It's required to assign to it. And if it's uninitialized, that is a construction. This means I have composable initialization guarantees because in the caller, the first green box, I know statically by local analysis only of the caller that, yeah, x is initialized on both branches, in one case by a direct construction, in the other case by being passed to an out parameter, which if it doesn't throw an exception, constructs it. And then in fill, again, separately, function local analysis, I guarantee that x is assigned to, which will construct it if it's not initialized, otherwise it will assign to it before it's used again in the rest of the function. So this is a composable initialization guarantee, and I have a generalized value set syntax. Now I showed all this last fall. I'm now I showed you half of the equals unification. This is the client side, the caller side. Now let's look at the authoring side. As I pointed out in the paper on parameter passing, an out this parameter is naturally a construction or an assignment operation because an out parameter can be initialized or not. Therefore, an out this is either a constructor or an assignment. It can act as both. There's also a that parameter. So this is special. It's always the same type as this class, and it's an alias for this object. That is the same, except it's an alias for another object. It's just really convenient and useful. So in the operator equals function, that is naturally a copy or move operation. I'm taking an object I can read from, but if I'm passed an R value, I can know that and automatically move from it. So here are the 4 combinations. Out this, in that, out this, move that, and then the same in, out, move. So you can still customize each one of those if you want to, but you don't have to. You can just write the first one because it's the general case that covers all four. In C++, we always like to be able to take control and overload and write the special purpose ones. You can still do that. No one is taking anything away from you. It's just a nicer default that I only have to write one function instead of 2 or 4. So this is the marquee function. Just to round this out, conversions also fit into this model because an out this parameter, which is a constructor or assignment from a single value of some other type, is a conversion, and they're explicit by default. You can opt into implicit if you want to, that's the opt-in, so we fix the default there again. And there's the simple sheet for conversions. If you're a visual person, and I am, here's how I view it. On the left-hand side, we have this. It's either out this, so the first row is all construction, or in out this. The second row is all assignment. Then we have an in that is copy, a move that is move, and something else is a conversion. So here are the generated functions. Are you ready? I can always generate assignment from construction. And the reason I can do this in syntax 2 is because they're all spelt equals. And because x equals something is the same syntax for construction and for assignment. This is super important. If I didn't have that, it's not just a syntax prettiness, it enables generic code. Remember, consistent syntax always enables better generic code. In this case, a generic operator equals. They can have these different meanings. I'll show you an example with actual code. And so that's this is generating assignment from construction. This is generating move from copy. Same thing. If the code for copy works, then if I'm passed an R value, I can just do exactly the same thing the copy function did, but just do std move instead. And in fact, that's how we already write so many of our functions. We cut and paste our copy function and then add the std moves and just take the parameter by R value reference. And if you want to do something different, you can still write both of them separately to do different things, but it's a convenient default. So here's an example. My class is a type. This is similar to what we saw before. It has 2 member variables. Name is a string, defaults to Henry. Address is a string, defaults to 1234 drive. And there's our single operator equals. That's all the copy and move functions and constructor as assignment. There's also a single operator equals, which is conversion from string, which is construct and assign from string. That is like this, another object of this type. There's the unified SMFs. There's the unified conversion function, explicit by default. Now, one thing I just want to point out, you know how in C++, constructors and assignment operators, if you don't write them, are member-wise by default? But once you write them, you have to do the member-wise part yourself? In CPP2, that except goes away. It's always default member-wise. So if in your unified function, or if you write a special assignment operator, if you don't mention certain data members, the defaults are still applied. So notice in the middle function, I comment out, it's as if I had written name equals that dot name, address equals that dot adder. And in fact, that's what's generated if you don't write it yourself. You can still write it by hand, but you don't need to. So here's that same function, or that same type. Let's squeeze it a little. By the way, these are all screenshots. Because they're PNGs, it's easy to manipulate them like this without messing with fonts. I think it's very important to show screenshots all the way through, because this is real code. This is not just PowerPoint. This is stuff that compiles, but doing live demos takes so long that it fills a talk, so I do screenshots instead, but they are screenshots. They're not just pretty PowerPoint. So the left is a screenshot of my editor of the CPP2 file. The right is removing some boilerplate, exactly what is emitted by cppfront from the left-hand side. So it emits class my class, okay. The name and address are private by default. You can see that the operator equals generates all 4 of the copy move construction assignment functions. And you can see that the conversion function gives you both conversions as well, construction and assignment. There's no bodies though, and that's because CPP2 is order independent. And the way I do this, as I explained last talk, is that I omit all the declarations, then all the definitions, so they can refer to each other. Slightly more complicated than that, but you do all the declarations, all the definitions, and you can be order independent. So that means that now the bodies come next. So here are the bodies of those 3.5 of the special member functions that they almost fit. And you can see how we generate the member-wise move and things like that in the member-wise copy, even if you didn't write it yourself. That's just the default. And that's standard C++ code. And then finally, there's the same for the conversion function. Notice for the conversion function, I initialize name. So I explicitly initialize name. I don't say anything about address because, I mean, I could say address and then repeat the initializer, but today's syntax already pulls it, so I don't omit that code because I know the compiler, that the language will already pull it. But it doesn't for the assignment operator, so I do inject it for the assignment. I took a screenshot of, zoomed out of my PowerPoint slide so you could see what it looks like side by side. I don't expect you to read the eye chart. To me, the important thing is that out of all of that, all I had to do was write that. And I got all this great C++ code that I would have otherwise written by hand. What about virtual functions? What about base classes? They're all about this. So because I now have an explicit this parameter, I can say whether it's virtual, override, or final, and you can say at most one of those. This, again, is simply giving language support for what we already teach. If you look at popular books, look at C++ coding standards, look at the C++ core guidelines, they already teach write exactly one of virtual, override, and final. Kind of sucks that today you can't even write them in the same place in the grammar, but you can still follow that advice today. But you can write more than one. You write them in different places. Here, there's one place to write them. You're required to write only one. It's simpler. There's less ways to go wrong, less to remember. And a base class, I thought long and hard about what's the best way to mention a base class. One thing I did not want to do is have a separate base class list. Just like I didn't, by the way, one thing I never mentioned here. Yeah, let's go all the way back here so I can, oh, it doesn't want to cooperate. Okay, I'm going to make you. All right, you PowerPoint, you. All right, let's go back to here. Now I forgot what I was going to say. Seriously, what was I just talking about?
You're talking about base classes.
Oh yeah, unifying the, so I already don't have a separate member initializer list here. I forgot to mention that. You might have noticed there's no meminit list. You're just required to initialize your members and, spoiler alert, bases in declaration order in the body of your operator equals. So now we can, boy, PowerPoint really fought me on that one. Okay, I know, I fought me because I programmed it, but yeah. So I thought, well, I know I don't want a separate base class list. You know, let me try this out. I'm 90% satisfied with this. This might change, but the way you write it is, this is a shape equal to, with this default value. So that's what a base class is. This is a shape. By the way, controversial decision come up. This is your cue to get ready with your pitchforks. I don't currently support non-public inheritance. I'm waiting to see whether you make me. Because I'm not convinced you need it. I'm not convinced I need it. I also don't support virtual inheritance. I will if it's needed. Certainly we can consume C++ types with virtual inheritance and non-public inheritance. They all work. There's no compatibility issue here. But I'm waiting to see whether once we have all the other refactoring, do we still need that? And if we do, then we can add it. We're definitely not going to lose any expressive power. I just want to be convinced before adding a feature that it's necessary in order to not lose expressive power. So currently today, don't be dismayed if you find that you can't write protected base classes, because we've never been able to find a use for those. Or virtual inheritance. I will add them if needed. I just don't see the need yet. But this is a shape. And so I don't know if I have an example of that. Oh, let's show a quick example. And last time, and I tried to demo GCC, the Windows subsystem crashed on me. So I'm going to see if GCC can have better airtime today. So let's go to some source code. Can everybody see that at the back? All right. Makes me want to say, can everybody see that? No. So here we have a main. And again, this is order independent, so I'm going to just, I decided to write it in the order I'm going to show it to you. So we'll start with main. I'm going to have a cyborg object. C is a cyborg, no initializer. I'm going to construct it. If you provide a command line parameter, I'll construct it with that name, args1 as stood string. Otherwise, I'll call it parsnip. That's why it's called parsnip CPP2. Okay, so here I've created a cyborg. You'll see what a cyborg is further down. I'm then going to ask it to print, ask it to speak, and ask it to do work. Now, CPP2 has unified function call syntax. When you say x.f, if that isn't available as a member function, it'll call f of x. And in fact, that's what's happening here, because there is no make, speak, or do work function on a cyborg, as you will see when you see its definition. But there are non-member functions that take what turn out to be base types of cyborg. So you can make a human speak. Make speak takes a human as an in parameter. And it says, OK, I'm going to now call, its function is actually called speak. So okay, I'm going to call the member function it actually has. This can be useful if you're writing adapters or examples on slides. And do work is going to take a machine that is just some gratuitously templated base class, and it's going to call the actual function, which is, and both of these are virtual functions. So let's see what these are. Human is a type where speak is a virtual function with no other parameters, and it has a destructor, a virtual destructor, and the convention I'm using for a destructor is move this. If you have a move function, like say you're moving from that, there's another parameter that you're moving to, like this. If your only parameter is move this, it's essentially saying move to nowhere. So I'm using that as my convention for a destructor. We'll see how it works out. I like it so far. So that's what human is. It's an interface that simply has a virtual function and a virtual destructor. And then in a namespace, just because I was testing that, I also have machine is a gratuitously templated type that has a conversion from string. It has a virtual destructor and a virtual work function. Now we get to cyborg. Here's what puts it all together. Cyborg is a type defined as follows. This is a human, so cyborg is a human, that's a base class. This is a machine 99, that's a base class. It also has name is a string, and address is a string that happens to have a default value. I have a conversion function from string, because out this is a conversion function, constructor assigned from another type, string, and it just initializes its base class. This is base class initialization. Now, because the base class is named this, I use the type's name. You write the type's name, and this is the only time you use the type's name. That's not a big deal. I do view it as a small wart, but it only appears there and everything else is elegant. So until I come up with a better idea, this seems like a reasonable approach to me. But I'm actually initializing the base class by using its name as the left-hand side. Then I'm initializing the data member as usual. That's the equivalent to saying this.name equals n. And then I'm emitting a message using string interpolation for name. Then I have my speak and work functions, which are overrides, so they override this. I have a print function, which is not virtual, but it's const, by default, just like the others are. Most of the others are. And it prints something about this. And then finally, there's the destructor that says, tired but satisfied after another successful day, name checks out and goes home to their family. So each prints something. And so let's actually see that works. So if I run my cppfront shell, which is going to invoke GCC, and parsnip.cp2, let's just do pure C++2 mode. There we go, GCC 10, and 10 and higher, so 10 works. That's the oldest version of GCC I currently support. And there we go, parsnip checks in for the day's shift. Parsnip lives at 123 Main Street. Now I'm doing that virtual call through that non-member function, which I invoked through member function unified syntax, which does the virtual call correctly, so we can see it's doing that correctly. Do work also prints a message, and then we get the destructor's message. So that gives you an example, sort of a toy example about how everything hangs together and how you express things. It's all things we express in C++ today, just with perhaps some different defaults. Const, for example, unified operator equals, but it's still C++, it's still invoking the C++ standard library without thunking, without overhead. So let's make a little change. Well, first of all, let's use a command line parameter. What would be a good name? Good name for our cyborg. I. Yeah, that works. So so we tested it. It's taking the command line parameter. That's good. But by the way, how many of you are from Commonwealth countries? So he's our king, right? Technically, still, I think. So a shout out to Charles. Yay, you had a big weekend. More about that in a moment. And because I can, I don't really have a use for this right here. But if you've ever used the boost facility to emit a base and stuff it in the member, take a data member and stuff it in as a base class, because it needs to be initialized before a base class, that's easy here. They're all in the same list. They're all in the same place. There's no more segregation of base lists and meminit lists. So all I need to do, if I want to initialize this string before the base class human, I just move the data member there. And then, of course, I still have to initialize in order, so I also have to move this initialization or it will complain. If I save that, rebuild, and it'll be fine. And if you look at the generated code, you'll see that it's actually taking that string name member and stuffing it in as a base class to ensure that it does get initialized before the other base class. But this is transparent to you. They're all in one place, so you can express them in the right order, which also affects data layout. You have more control over data layout. You have more control over object lifetimes and dependencies. And the fact that there's a boost utility to do this shows that there is a need. So now let's talk about metafunctions. This is from a talk I gave in 2017 about metaclasses. I now say type metafunctions, same concept. And it's pointing out that Bjarne created a really, really powerful thing with the class. The C++ class can express all of this universe of different possibilities. There is no separate notion of an interface like there is in C# or Java or other languages. It's an abstract base class that has only pure virtual functions and a virtual destructor, right? We can express Corba interfaces, COM classes, value types, C structs, pods, variants, enums, properties, flag enums, single inheritance bases, multiple inheritance bases. The problem is we do it by convention, by rote, by rule. So it requires more boilerplate. We can make mistakes. It's inconvenient. What if we could declaratively say that we are building one of those and pick one? And actually just write in code, well, what are the characteristics of this subset of the universe of all the classes I could write? It's still a C++ class at the end of the day, but just apply different defaults or generate some functions for me. So here's the example that I gave where the language already does this. So you write the code on the left, and the language writes the code on the right for you. This is happening today, and it's been happening for years. But it's the compiler that has this, essentially the pseudocode, but you can write what it is. It's just specified in standard ease. But it's like a compile type metafunction, but it's hardwired, and you only get one of them. And this is why we have so many problems with generated defaults in C++, is because there's only one, and one size does not fit all. Those generated functions are great a lot of the time, but not when you're writing something different from, say, a value type. And that's why we need things like equals delete to get rid of them when we got the ones we didn't want, or when we had a raw pointer member and we got copying and, oh, that's not really the safe thing to do. So what I said those years ago, because I had designed this for CPP2 then, what if you could write your own code there to give a name to a group of defaults and behaviors? Now, let's get rid of the scary ghosts here. We're not making the language grammar mutable. I'm not giving you new ways to write new language grammar, no. I am not making definitions mutable after the fact. ODR rules. You're not making definitions mutable. It's just in that little narrow window, right after the compiler has parsed your code, you've got the parse tree. And right before the very next statement where it says return it, and there's your one definition that's never going to change, right in there, there's now one extra hook saying, by the way, here's the parse tree. Would you like to adjust anything? And when that returns, it's cast in stone as usual. It is a very, very narrow, disciplined, safe hook. It is not a mutable language. It is not causing ODR problems. It is giving you a hook to write code that normally your compiler writer would have to write that simply participates in interpreting the meaning of a class. And it's entirely opt-in. So here's the example I gave. In the C# language, this is a screenshot. It's about 18 pages of English to describe what an interface type is, because it's a different type hardwired into the language. And I said, and I showed with a prototype written by Andrew Sutton and Jennifer Yao and Wyatt Childers, thank you to them, and then to others for further prototypes. Here is what we could write as a roughly 10-line metafunction, which runs as I described, and applies those defaults. It requires there's a destructor, and that it's virtual, that every function is virtual. It requires that there are no data members. It requires that there's no copy or moves, and even gives a helpful suggestion as to what you should do instead, because it knows the kind of type you're writing. This is the code I showed in 2017. This is the code I checked in about a month ago and described in my blog post. I actually split this out into a separate function because I was reusing it for more than one metafunction, but I put it back for the purpose of here so you can see the whole thing. That's the code from a week ago. And that now compiles and runs and does exactly what I said. And I'll show you an example in a minute. But there's an update. That was so 1 week ago. As you might have noticed, a lot of things happened this weekend. We have, if you're from a Commonwealth country, that's we. I live in the States now for 20 years, but I'm from Canada. I'm a Canuck, eh? So we now have, I think, all of us, a new king, Charles III, and let me make sure I'm getting the title exactly right, Queen Consort Diana II. Too soon? No, but seriously, what happened this weekend was that in the wiki list on the cppfront repo, sorry, I'm losing my breath in the air here. We're getting high on the air. This is the highest altitude talk I've ever given, including without a microphone. So this is a screenshot of the cppfront wiki, and where I list some companion projects. The very newest one, which was just made available on Saturday, thank you, Joel Ernesto Guerrero Peña, was a Clang format fork with CP2 support. So thank you very much, Joel, for that. He also did the CMake module support, which allows you, which actually works in Godbolt, and it's how you execute CPP2 programs in Godbolt. So thank you for that. Also, I started self-hosting. So 48 hours ago, all of CppFront was written in C++20. As of right now, I started with the reflect header. And as of right now, most of that header, which is about 3% of all CppFront, so it's only 3%, but hey, it's only been 2 days, is now written in Cpp2 and is self-hosted. So it was an interesting exercise to start doing that. And what that means is that as of 2 days ago, this is the code for interface that's checked into the repo, which is written in Cpp2. And it looks very much like the other code. If I put the slides side to side, you would notice that they're in slightly different fonts because the parens are a little different. And that you actually notice that shows how similar the code is. In my blog post last week, I gave a couple of examples of using metafunctions, and here's how you currently apply them. Shape is a type, but I'm going to apply a metafunction. Shape is an interface type. And yes, I've long liked the adjective syntax ever since I led the design of C++ CLI interface class. I'm at it again. Shape is an interface type with these members. And that requires and declares up front and enforces that there's going to be no data members, otherwise you'll get a compile time error. You're not going to get copying functions. They don't make sense for interfaces. You won't get implemented functions. I might relax that to make it not pure virtual because maybe sometimes you do want to implement some functions in an interface, but without data, what does that really mean? And a public pure virtual destructor, but here's the important bit. The word interface carries all that meaning. It is one word that ties you into a bundle of opt-ins you will never have to equal delete because you asked for them. And it's safe, and it's simple, and it's efficient all at the same time. I didn't have to go to a language design committee like the C# committee and ask to introduce an interface concept, wait for it to be approved, wait for my compiler vendors to implement it as a language feature, and then get to use it. I'm pretty sure that the interface that I showed on the previous slide, that dozen-line function, is equivalent to those 18 pages of C# specification. And it's testable code. And it's not a language feature. When you can enable someone to write, this is why classes are such a big deal. Bjarne let people write a new type that carries a bundle of behavior and capabilities all encapsulated. That means I can write a class, I can write a word of power. This is that. I can write a word of power without hardwiring it into the language. Here's another one, and again, I'll skip most of this, but point2d is a value type. And as you'll see, a value means it's totally ordered, so it has operator spaceships, all the orderings work. It's copyable, it's movable, and a few other things. Without hardwiring the concept value into the language. That's safe, that's simple, that's efficient. That's the code I want to be able to write. So here are the ones that are implemented so far. This is the same list that I showed in my blog post a week ago, except that I refactored out copyable because I needed it myself in reflect.h. So I just split basic value. Half of basic value became copyable, and basic value invokes copyable. If you look at value, value is an ordered basic value. I like how these adjectives work well together. If you are of the camp of people who believe that a regular type is not only a default constructible, copyable, movable one that has no virtual functions, and you think, and it's comparable, because that's a big debate about is regular comparable, then value means regular to you. That is a regular type. And I can declare it and get all those defaults just by saying point2d is a value type. So here in a nutshell is how that looks. If we go back to that same example, let's just go to those base classes. There we are, human. So you notice I had to write virtual this. I had to write my destructor. I could just get rid of this virtual and let that be a default. And I could let the destructor be a default and just make it that if I declare this is an interface type. And let's see, machine. That's a polymorphic base type, which means, let's see, I still need this virtual because polymorphic base can have non-virtual functions, so virtual isn't a default. Oh no, so I still need this virtual, but I don't need this virtual destructor because polymorphic base requires that you have either a public virtual destructor or a protected non-virtual destructor, which is straight out of the C++ guidance literature, including the C++ core guidelines. I think I wrote that in the core guidelines. I'm not the only one who wrote it in places. So if I don't write a destructor, I'll get a pure virtual one generated by default. Let's save that. Whoops. And then let's go run it one more time. And let's give Charles a rest and go back to parsnip, and it works fine. So that's an example of applying defaults where I think that a lot of the time, call me a Pollyanna, I just from experience think a lot of the time, if you can find the right abstraction, and that's a big if, but if you can find the right abstraction, that simple, safe, and efficient are not in tension. Bjorn has been proving that with algorithms since the 1980s and 90s. I think it's still true. But let's talk about compatibility. I want to quote John Carmack. This is from an article that he wrote about a decade ago. It made its rounds on Reddit a couple months ago again. But John is I think everybody knows who he is, id Software, Doom, and many other things, Wolfenstein. He's also very pragmatic and seasoned as a software developer. He understands that a language does not exist in a vacuum. When we write software, we do much more than use C++, the language spec. I'll use his words. He says, and he was talking about functional programming specifically, I do believe there's real value in pursuing functional programming. You could say safety or something else here. But it would be irresponsible to exhort everyone to abandon their C++ compilers and start coding in Lisp, Haskell, or to be blunt, any other fringe language. I agree with him. And he was just picking on functional programming in that particular post and then showing how to do it in C++. But it's true of any new thing. We should first be looking, how can we do it in C++, even if it's hard? He continues, to the eternal chagrin of language designers, there are plenty of externalities outside the language that can overwhelm the benefits of a language. A language can be pretty, a language can be sweet. But one of the huge advantages of compatibility is you don't have to bootstrap your own ecosystem. And those few words carry man, person, centuries of work along with them. He continues, we have cross-platform issues, proprietary tool chains, certification gates, licensed technologies, and stringent performance requirements, on top of the issues with legacy code bases and workforce availability that everyone faces. Sean mentioned it in his talk this morning. Having more than a single source compiler for Rust, having a language spec. That's just the beginning. We're starting to use Rust at Microsoft. Rust is being handled by part of the Visual C++ team. So I get a fair amount of visibility into the work that's been going on for several years now. And we're still in the early days of, but here are these massive complex tool chains, and we've got like this 10% that actually work with Rust, and we got to make this tool that we rely on work with Rust, and we got to make this library rely with. It can be done, but it is a huge adoption barrier. A language is much more than a syntax and a specification. When we look at a new language, the cost of actually adopting a language is enormous, and most of the cost has nothing to do with the language. Now, Rust is getting good traction. It's still 1% the size of the C++ developers in the world, and it's been out for, I think officially now, for over a decade. That's how long things take. Decade. Hold that thought. I gave a talk 3 years ago, in the early days of the pandemic, Bridge to New Thingia, and the subtitle was explicitly, how to answer why will yours succeed when all these other projects that look a lot like that thing you're trying now have failed. Adding safety to C++ was one of the things specifically in my mind 3 years ago, the reason I wrote this talk, although I didn't mention it specifically. I noticed on Reddit, by the way, some committee member said, he wrote that talk to say that ABI safety decisions should go a certain way. Yeah, compatibility also applies to ABI, but that never occurred to me. I was interested in safety in CPP2 and evolving C++. That was why I gave this talk. So if you want to rewatch it, it's a short talk, half an hour, C++ on C. You may have a different perspective on, that's what the subtext was. It may have different meaning to you watching it again today. But here are some highlights. I mean, right? I don't need to say anything. The picture tells the whole story. I'm told there was somebody tried to do a JavaScript, the good parts, but let's not go there. I mean, one is a home defense weapon too, but this was the motivation for many languages. Two among them were Dart and Typescript. There was a clear problem to be solved. So the first thing I said that you want is a clear elevator pitch. Typescript and Dart said, this complexity with JavaScript, we love JavaScript, but that complexity is too much. We can say what the good parts are. That's the problem we're going to solve. Bjarne Strustrup, when he created C++, said, we love C, want to be fully compatible with C, but it doesn't have abstraction. That's the problem I want to solve. That's a 10-second elevator pitch. Never mind 30-second elevator pitch. You should be able to give a 10-second one. And the easiest way to accomplish that is to point to a well-known problem and say, I'm solving that. This was a well-known problem. That's how you get to a 10-second elevator pitch. That's the problem. Yeah, I know. I'm solving that. I already know a lot about what you're trying to do. Tell me more. There's a problem, though. If you look at the effort that you put into adopting something new versus the value you see, which adoption function would you prefer? As a user or as a producer? That one on the right looks on the left looks a lot like a wall, because that step is so big that it is a wall. It is essential if you want to have a shot at competing with, replacing, evolving any old thing, any existing thing in any industry, in any domain, to have high fidelity compatibility with that thing. You can succeed without it, but I'll show you how much it's going to cost you, because it's quantifiable. The minimum bar in our language world is that new thing can seamlessly call old thing. No thunking, no wrapping, none of that. So a good compatibility is that it's a step function, but with smaller steps that aren't walls. So that a customer can put in some amount of effort. They haven't seen any value at first, but then after a day or a week, then they start seeing some value. For example, if you can say in your existing language project, in your JavaScript project, you can add one new file of my new language, and it interoperates with everything, but it's got to be in its own separate file. That's already a really good adoption story. It works in any JavaScript project. Oh, okay, that's easier to adopt. Tell me more. The grail is in that existing project, anywhere inside it, I can write one new line of code in the existing files and start seeing benefit. That's the holy grail. This has been done before. Bjarne did it. Rename any .c file, this mostly still works today, to .cpp, add one class, you're already starting to see benefit. Super, super important. That, more than most things, is why C++ won out of all the language wars of the 80s and 90s. In the 2010s, rename JS to TS, add one type definition, and you're already seeing benefit. That is the holy grail. And ramps are great. They're not just for old folks. So C++, every C program, this is still mostly true, is a C++ program. Any C++ code can call C code seamlessly, no thunking, no interrupt, no marshalling, none of that. and any of it, and takes advantage of the C toolchain, the optimizer, the linker, especially cffront did that. TypeScript, every JavaScript program is a TypeScript program. And any TypeScript code can seamlessly call JavaScript code. Why? Because they transpile to it. And as Bjarne is fond of saying, because he got all this in the 80s for, oh, this is transpiler. Transpiler is a compiler. It's got all the same phases. It just lowers to another language instead of to IR, or IL in the case of the managed languages. Every user of TypeScript uses a transpiler in production today. Swift has a similar compatibility story with Objective-C. Roslyn at the tool level, C# environment, C# compiler, also had very similar strict compatibility requirements, had a very similar story with the previous compiler it was replacing, and therefore succeeded in doing a fairly quick replacement. Let me just talk about TypeScript just for one more slide. TypeScript is fully compatible with JavaScript. It emits JavaScript. So TypeScript has always had the story that, hey, you know what? Try TypeScript. You can write one line of code in your JavaScript file, just rename it TS, and you still have JavaScript, which means if you ever don't like this, just throw away the TypeScript and you always have your JavaScript. Super, super compelling and important story for adoption. That's what compatibility means. Zero marshals, zero overhead, no wrapping, no thunking. They cooperate with the JavaScript committee, the ECMAScript committee. How many of you knew that TypeScript designers go to the ECMAScript committee? A few. A lot of people would just assume, well, that's another language. Why would they do that? It's because they don't view themselves that way. It's not where their hearts are. It's not their goal or objective. They contribute proposals to JavaScript. In many ways, TypeScript has been testing out proposals for JavaScript itself to evolve to. And TypeScript features are today in standard JavaScript. And everybody's happy with this. What I'm showing you so far on this slide, I checked on the weekend, just like, hey, you know, I'm not saying anything wrong here, right? And I got a reply back, yeah, everything is correct. So that has been fact-checked. What I'm about to say is only my personal observation. I have not validated with anybody. You are the first people to see this slide. This is just my personal opinion. I think TypeScript loves JavaScript, and it doesn't seem to me, and this is the important part, it doesn't seem to me that the TypeScript designers view TypeScript as a successor language. And that's why they're successful. There are other attempts to do a better JavaScript. Dart was one. But the problem with all of these others, not just Dart, was they were something different. And there were different levels of compatibility, but they were never a stake in the ground from the beginning, must have 100% pure compatibility. There's never a stake in the ground for them. And to this day, so I showed this slide when I gave the Bridge to New Thingy talk in 2020. I then updated it by looking up that same issue number, still open, 3 years later. It is really hard to back into compatibility, because unless it's a design goal from the very beginning, you're going to compromise it because it'll make something easier, and you will never be able to get fully back to it without restarting, without starting over. And nobody can ever afford to do that unless you have no users. Let me give you some examples of time frames. So I joined Microsoft a couple of years after, about 4 years after Visual C++ 6 was released. And they were busy getting ready to ship 7.1. And even then it was like, you know, so many of our customers are still using 6. They haven't even gone to 7. That ended up being the story of my first almost decade at Microsoft. Because Visual C++ 6 was popular. More popular than its successors. And to the point where in 2010, we actually, because we were on 3-year release cycles then, these t-shirts were actually worn at the PDC, I think we called them PDC at the time, of 2008. The product wouldn't be released for 2 more years. But we had t-shirts made up that we all wore them. 10 is the new 6, like version 10 is finally going to replace version 6 because we're going to address these compatibility problems. And it was compatibility regressions. Binary and sourcing compatibilities did not help when you have them together, but also usability regressions. People found it was just pig slow. No offense to pigs, but it was really caterpillar slow. And compared to people saying, even in the late aughts, I can still build my MFC project faster in Visual C++ 6 than in Visual C++ that you're shipping today, which is embarrassing when it's true. So we ran this survey last month, and we asked, one of the questions in the global developer survey was, what programming language environments do you use in your current and recent projects? So people asked, what other languages do you use? Do you use C++ programmers? If you had to name C++'s sister language, the one that by far the most popular language that C++ programmers use, other language, what would it be? So I heard a little bit of C, but not until the Python people gave the right answer, because you'd no, but seriously, because I would have typically thought C. I thought C for many years. Well, look at the compatibility. I use C libraries all the time. For years now, always Python. Over 70% of C++ developers who responded to the survey this year, and the numbers were similar last year and the year before that, also use Python. So if there is a sister language to C++, that's the one. Here is Python's release history from Wikipedia. Notice, do you notice any non-smoothness? I was considering putting up this slide first without intro and asking you which language is this, but it's probably too easy. I want you to look at those dates. Python 3 was released in 2008. It was a source-breaking change. Now, I'll give you an example. My favorite example is 3/2, not because it's Python 3 and 2. It's just, I noticed that afterwards, but it's a good joke, so now I'll point it out. 3/2 has value 2 in Python 2 and has value 1.5 in Python 3. I foresee no problems with this. I'll just port my code and run it. Well, and also there were syntax changes where its syntax was not necessarily legal in one direction versus the other. But there were all sorts of manual migration tools that did, and many of them were quite good, gave you 95% of the way there, which as it turns out leaves 95% of the work for you still to do. Like 95% really is not good for automatic source migration. 95%, ask anybody who's used a C++ modernizer. 95% is a good start. Now you've done a prototype, now do better. Also, a red flag is that there are so many of them. And it's because of that problem. As late as 2017, most Python code the majority of Python code was still written in the intersection of 2 and 3. Finally, in 2020, it was frozen. And this 12-year transition, this is the JetBrains survey, thank you, JetBrains. In 2019, we were finally down to 10% of Python users saying they used Python 2x. That's 1 year before it was not only end of life, but end of security fixed. Actually, it was months before that. There were still 10% of people using it. So I remember I mentioned I happened to be in a meeting. This is coincidental. I happened to be in an unrelated meeting last week with Guido. Guido was one of the people in the room. And when I noticed his shirt, I said, okay, Guido, I'm giving a talk at the C++ conference on Monday. Can I take your picture? Because that shirt is just perfect. And he said, okay. And so he vetted all this and he allowed that. Thank you, Guido. He's very gracious. But you'll notice the thing about the shirt. This shirt is actually about 6 years old. But at the time, that was around 3.7 came out. This is like their 10 is the new 6 shirt, right? Like seriously, because they're saying like, now upgrade to 0.7. 3.7, not 2.7. Like just bump your major version number instead of your minor version number because there had already been 7 releases of 3 and most people were still on 2. 7. It took longer than that, though. And now this is a quote going back to, I think it was last year. Maybe it might have been the year before, but I think it was last year. One of the first times where I talked just one-on-one or two-on-one with Guido. And I just asked him, I know he's super smart. He's been through a lot. This was not critical at all. It's just like, you've lived it in the trenches. You've gone through that. You've taken a huge community through a huge transition. 2 to 3, you've succeeded. Is there anything you would do differently? The words were barely out of my mouth when he said, we would do everything differently. We totally underestimated the cost of compatibility. We thought it would be way easier to move people onto the new breaking change syntax. We had no idea the costs involved. If we could do this over, we would do everything differently. So let me point out the Python release history. Again, thank you, Wikipedia, so it must be true. And you'll notice that there's 3.7, which he was wearing the shirt about, so it's from about 2018. It was released in 2018. And 2.7 was end-of-lifed in early 2020, and yet a few months before that, you just saw 10% of all developers were still using it. In fact, to this day, 3 years after it has been not getting security fixes, I know for a fact there are still regular new security fixes to fix CVEs requested for Python 2.7. And they are refused unless, I don't think I'm saying anything secret here, but it's an observation because everything's public there. But you may not have noticed, if you really need a security, a CVE patch in Python 2.7, which we will for a long time, unfortunately, the way you justify it is point out that the CVE has been fixed in 3. That actually is an argument they listen to. They say, okay, if they fix it in 3, we'll fix it in 2. That still happens. But it's unofficial. It's not guaranteed that you'll get those fixes anymore because we're already more than 3 years after 2x said, we're not going to give you any more security fixes. And they still are, but you have to ask real hard. You know how sometimes you see something that you can't unsee? Now, this may sound a little weird. I know how this will sound. But we all know that when you take a popular technology that is an end-of-life security for it, and refuse to give it more security updates, especially when that is a popular technology used all over the internet, you're going to get more viruses, right? So I know there's the lab leak theory, and I know there's the animal spillover theory. Now, I'm not saying, but I am going to say that I know C++ was not the reason that all our kids were stuck at home for 2 years. So C99 had a similar story. They added complex and VLAs in 1999. They had to roll them back officially. They actually added optional features to the standard and retroactively applied them to those 2 features in C++, in C11. And then C++, we've been pretty compatible, but remember basic string when we said it couldn't be copy on write anymore? We said that in 2008. We voted on that as a committee. We shipped it in 2011, C++ 11. GCC 5.1 first shipped a conforming std string in 2015, and it wasn't until 2019 that a major Linux distribution finally enabled it by default. How many years is that? Have you noticed a pattern? This is what a decade looks like. This is a decade's worth of calendars. Visual C++ 6 took about 12 years to displace from the market because of incompatibility. C99 took about 12 years to make optional the features that not everybody was implementing in compilers because of compatibility. C++11 string took 11 years, yay, we saved a year, to be on every major Linux distro by default. Python 3 took 12 years to get to over 90% of its users. If you don't build a strong backward compatibility bridge, you might still succeed, but it's gonna take you a decade longer. It always does. And of course, that decade to a fledgling project means risk, because that's how much longer you have to keep asking for funding and justifying your project. And those of us who've been there know how painful that is. Compatibility, if you don't have it, will cost you a decade in adoption. It always does. Somebody once said that every time you take a sharp turn, some people fall off the bus. And I'll just add to that, sometimes the bus actually falls over. So let me point out that if you start with a status quo language like JavaScript or C++ or Objective-C, because Swift is another good example of doing it right, the typical way we evolve, the hard but still easy way, is to do what I call the 10% plan. We're going to make percentage-wise, like 10% improvement per release on some dimension. We might pick a different dimension each release, but think of it as the incremental improvement, the 10% plan. That's the default for existing evolution. It's what ECMAScript did for every release except 4, which nearly broke the committee because they started adding incompatibilities. It is what Python 2 did before 3, and it's what 3 has done since, and it's what C++ has always done. So what if we actually want to get a 10x improvement? Because that's what we're here for. That's why we're having so many talks at this conference about how do we get a 10x improvement. The default plan there is to design something new. And there's nothing wrong with that. In fact, that's easier than adopting the constraint of compatibility, because it gives you much more flexibility in design. You can fix more things and have a really nice design in many ways. It is competitive. It will have limited interoperability with the existing language because it wasn't a design make or break stake in the ground from the beginning. And it will be source or binary incompatible. Dart is an example of that. Now, by the way, I'm going to call this the Dart plan, but that is not intended to be pejorative. I know that there are political things I've heard with Dart. I don't know the details. I don't want to. Simply at a technical level, these incompatibilities certainly contributed to its lack of acceptance, and in my opinion, must be the most important technical factor, even if there may be other factors. But it's not just Dart. ECMAScript 4 nearly fell in that hole. Python 3 fell in the hole. And I could list you a lot of these. Some of these are internal Microsoft languages that may or may not have ever been mentioned, and there's a whole slew of these. I have seen them over and over try to build something new, and then go back and try to build a compatibility bridge later, and you can't. You might wrap some things, you might wrap popular types from the standard library or something like that, but you'll never get there without starting over because it wasn't a design goal from day one. But TypeScript and Swift, I'll include Swift in this category, we're on a compatibility plan by fundamental design choice. They were cooperative with the existing language. Well, both TypeScript and Swift were. Swift had helped that one company was the major owner of both. They always had seamless interop with the language that they were trying to improve and get a 10x improvement for. They were source and binary compatible, including in Swift's case, the arc reference counting that was added to Objective-C came from Swift before Swift was introduced, before Swift was publicly announced. The object models are a superset. That's what compatibility looks like. So far, nobody has tried this plan for C++, except for C++ itself, C++ Next. 23 is just as compatible with 20 as TypeScript is with JavaScript. And I aim to fit in that. That's what I think is worth doing. In fact, if I could just adjust this a little bit, I think this might be a bit of a closer, because you're actually much closer to doing an evolution because of that strong compatibility tie. But there are extra costs both ways. If you do the Dart plan, you're going to be wrapping forever. You're going to be having incompatibilities forever. I already showed you the Dart ES compatibility, GitHub, open issue, and there's more where that came from. You're going to be in wrapping mode. So C++ WinRT is having this problem right now, calling native libraries, package.js. If you do the TypeScript plan, you'll also have costs. They're costs of cooperation. It takes time to show up at standards meetings for the existing language, whether it be ECMAScript or C++. It takes time and energy to cooperate and participate in that language's continued evolution instead of forking and competing and doing something incompatible. It takes time to contribute evolution proposals to that language's evolution, but it'll save you 10 years of adoption if you succeed. So the end of my talk, Bridge to New Thingia, was to answer that question. And so the C++ on C version, I ended this way. I summarized the three things. Value, have your elevator pitch by pointing at, there's that pain point that's well known. I'm going to solve that. Availability, that you work wherever the existing thing is being used today. And seamless backward compatibility. You can't back into it. If you don't have this, expect to slow your adoption by a decade. A good answer is I can use new things side by side in the same project as old thing. The grail is I can write one line of code and start seeing benefit in an existing project of old thing. And then I actually added this slide. This slide I showed at C++ on C. Now, I'm adjusting my use of the word successor because when I said successor here, notice I was including C++23. It's lately been used to mean an incompatible successor. But here I intended it to include a super compatible successor that is essentially an evolution of the original language. What does it take to be successful? So I said this 3 years ago. It takes, you got to show the value very clearly. Say it in 10 seconds. We love C++, but we're going to solve safety and simplicity. Something like that. Be very clear about what you're solving. Not just we're going to make things better and then have a long list. That's not clear. It has to be available. Should work with all existing C++ compilers out of the gate. And to answer that question fully, why will your thing succeed when C cured, Cyclone, C flat, C natural? There's been so many attempts to make C and C++ safer, mostly C, because C++ is harder. Here's a differentiator that until now, only C++ itself has tried in successive versions of the standard, because it's legit difficult. Have seamless backward interop with no qualification. It just works. I will be able to use, yeah, we changed the meaning of auto and broke like some 1 in a million lines of code. That's incremental breakage, but that's the level of noise breakage that you can tolerate. If you don't have that, you might still succeed. There's nothing wrong with trying an incompatible Dart plan. You may still succeed, but it's going to take you 10 years longer. And the good and the grail are the same, as I said. So I thought, well, nobody's tried this. I'll give it a shot. And I may still fail, because there's lots of reasons you can fail, even if you get some things right. So even if I'm right about this, which I may not be, there's still lots of other ways to fail. So that's how we keep exploring ways to fail. Light bulbs that don't work until he found one that did. But this is why I've been bringing language proposals one at a time from CPP2 to the C++ committee for the last 8 years. I'm very happy that one of them is already in the standard. I think that's the right idea for cooperation. So how would I fill in this blank? There's actually 4 words that come to mind. The 3 we've been talking about a lot, but the one I'm going to leave you with. The 3 we've been talking about a lot is safety for C++. It's super important. We're going to have a panel on it, hopefully not with 13 chairs, after dinner tonight. Talking about simplicity, especially for humans, for the programmers who read and write the code. We've talked about compatibility for C++. Maybe you thought that was the one I was going to finish on, but it's only one of the 3 contributors. The thing that, to me, and again, this is just my personal opinion, but what I exhort you to think about and perhaps consider is really the union of those 3. And the way I phrase it is, I would like to see if we can do a TypeScript for C++. I have been thinking with that exact phrase for about 5 years now. But this is the first time I'm saying it publicly on stage. But I hope I give the reason why, and I don't worship at the altar of Anders Hejlsberg, even though he's the only person, I think, in the history of the planet who has designed multiple million user programming languages. I mean, that's impressive. He just really knows how to do a good job, and compatibility was important to him. And he understood the importance of cooperating, of being compatible, and the benefits that come from that. So we've seen what it can do. Swift is another. You can fill this in if you prefer with a Swift for C++. Notice Swift is for Objective-C. I know there's a talk also today on Swift in C++, and it's fine. That's the Dart plan because Swift was designed for compatibility with Objective-C. Applied to Objective-C, it's a TypeScript plan, and it has been working very well. Let's see if we can pursue a TypeScript for C++. There's a lot of value in the plan, and certainly C++ needs a 10x improvement. This plan is known to work. I think we should at least try. That's what I'll leave with you today. Thank you very much for coming.